Hello, and welcome back to Stat 3050 online. We are indoors, having a good time, per usual, right? Per usual. So today, I have a little example on quadratic regression. It sounds complicated, but it's really not. In fact, it's so simple, right, that I only have three goals. The first one being identifying curvature in a scatter plot. And then modeling that curvature. It might make sense to model curvature, right? In biological sense or natural sense, who knows? And then the last one, I've sort of got this idea of multiple regression in R and interactions that I want to introduce. Interactions can get a little tricky, but multiple regression in R is fairly simple. So I kind of show you how to get all that going. And then per usual, we've got some sponsors, which in this case is High Energy Elevator Music. Two just absolute killer albums. So good, both of them. Emily King and Corey Wong, good lord. Just cannot get enough. Cannot get enough. All right, let's go to R. So today we're going to be working with some wind turbine data. Wind turbine data, wow. And so what it is, and actually let me read it in here first. So just like always, we're setting our working directory, and I have my data stored in simple regression. So I've got that, and I believe I've called it wind.csv, and you can find this in the class folder or online, so you can work with it too. But here's what I'm doing. So I'm gonna read in the data. And I'm gonna do that. I'm gonna call it wind just for fun, right? And then I'm going to use this read.csv function, and then I've got it called wind.csv. And then sometimes I do this, sometimes I don't. I'm pretty bad at being consistent with this, but this header equals true. Just make sure that the first row of the CSV file is actually the column names. Okay, so we read that in, and here's what we got. Okay, so we have two columns. Well, we have three columns, right? Something went funky with reading it in when it was stored as a CSV, but that's fine. I'll show you how to get rid of that. But we have two columns that matter, wind velocity, wind.velocity, and DC output. So this is like an energy output of a wind turbine, and this is the wind speed, right? So pretty much how fast it's blowing, and then how much energy is being produced. So the first thing we want to do, just for ease of working, is we want to get rid of this third column here. And it might not be there for you, it is for me. But all we're going to do is we're going to say wind, we're going to get that same data, we're going to call it the same thing, and we're going to use the data from wind. We're going to use this square bracket notation. And so recall that the square bracket notation is row and then column, right? Row numbers and then column numbers. But I want all the rows, so I'm just going to leave that blank. I can even put a space there. And then I just want rows 1 and 2, and I can say rows 1 through 2 and be fine, right? I could also do this, C, concatenate 1 and 2, but for now I'm just going to do this, and we'll see over here the number of variables have changed, and it's just our two friends, wind and power. Okay. Well, so what's sort of the first thing to do? Well, the first thing to do is make sure that the structure of the data is fine, which it is. We've got two numeric variables now. Nothing is being stored as characters or factors or anything like that, so that's good. And then maybe hitting it with sort of just the summary function, just to see what exactly is going on. And we see here the sort of traditional 5, 6-ish number summary of each of the columns, right? We have the min and the max and the mean and the median, whatever. Sort of eyeballing to see if the mean and the median are around the same number, which in this case both of them are. So that's good. That's good. So what do we want to do first? Well, let's plot the data. Since we only have two variables, it's pretty easy to do that. And I'm going to use a scatter plot. So we read in or load in the tidyverse library. Okay, so that's good. Got everything there. And then we'll use this ggplot function. And the data is just going to be wind. And the aesthetic, the x and y variables, we want to predict or at least find the relationship between wind and velocity, velocity, wind velocity, and power output. So our power output is going to be some function of the wind velocity, right? It doesn't really make sense to make velocity some function of power, right? It may, but in this case we want to see, how output is a function of the wind speed. So that means that our wind speed, our wind velocity, is going to be our x, and then our y is going to be DC output, I believe. Let me make sure. Yeah, it's all caps. Cool. So if we run that, we'll see a totally blank, mapped out variables, but nothing actually there. So what we need to do is this geom point, leave that blank, right? There's really nothing that needs to go in there, and then geom smooth. And remember that, well, in this case, let's just see what a straight line looks like. Let's just see what that looks like. Okay, here we go. And actually, let me get rid of this background here just to make it a little bit easier to look at. So what do we see? Well, we see that the straight line is doing an okay job at modeling the data. It's okay, but we do sort of see this curvature upward. And let me actually zoom it in here so we can see. I see some evidence of this sort of like parabolic nature, right? So it's sort of flattening off here, and who knows, it might go downward. We're not too sure. But for right now, we see that we have a lot of data that's underneath the line over here, a lot of data that's above the line, and then more data underneath the line as you go further out. So that's something that we want to keep in mind, and maybe we want to see what that curvature actually looks like. So we'll use this lowest function, this lowest type of line drawing, and we see here. Yes, nice. So we see here, very nice looking curve, right? Very nice looking parabolic curve almost, right? Or maybe this sort of quadratic thing, right? So we now see that this line is doing a better job at sort of mapping the data or sort of describing the data at various points, right? We don't see too many points below the line, maybe a few, and we don't see as many points above the line, I should say. So looking at it, it's got this sort of curve. Maybe we want to model it in like a quadratic kind of way. So how do we do that? Well, let's plot it first. Plotting it as, this sort of x plus x squared kind of situation. That would be y equals x plus x squared, right? Okay, so how do we do that? Well, we'll do the same old. In fact, I'm just going to copy and paste this. I'm not even going to worry about typing it all in and wasting your time. And then my hands are kind of cold right now, so less typing the better. We'll turn this back into LM for linear model. And the only thing that we need to do extra is say formula, very similar to the regression side of things, right, when we're modeling. But this formula equals, and we put it in general terms. So we put it in general terms. So this y as a function of x plus, and then very important that we use this capital I here, just so the variable gets treated as is, right? We write it like that. So x plus x squared, right? We just have to put that x squared in this kind of notation. Everything else is fine, so we run that. So what do we see? Well, we zoom it in a little bit, and we see now that that sort of lowest shape, what that lowest line was doing, is being sort of emulated here, right? It's being sort of reflected here. So we see that this data looks a lot better. These data look a lot better when you have this quadratic sort of function mapped on top of the data. Okay, well, so let's just say that this is fine. We're okay with exploring this idea that it's maybe an x plus x squared situation. Let's model it that way. So how do we do that? Well, maybe we want to model it first as just a straight line. So I'll call this model 1, and it's going to get a linear model with the formula, and this time we have to use the data-specific formula, DC output as a function of wind velocity. And the data is coming from wind. Very cool. So we run that, and we hit it with this summary.lm, model 1, and what do we see? All right, here we go. So we want to, maybe we don't know what our purpose is, but maybe we want to at least have significant values or significant p-values, I should say, for both of the beta coefficients. In this case, the beta naught, the intercept, and then beta 1, this slope. And we see here, when we move over to the p-value, we see a p-value of 0.31 here, and then a very low p-value, almost 0, right? So this is an issue, right? Our intercept is not significant. Our slope is this linear situation, but our intercept is not. And then we come down here, and then we say, okay, the multiple r squared and the adjusted r squared, they're both right around the same value, right? There's not a huge difference between the adjusted and the normal r squared. So this is not good, right? This is not good. We want to have both significant terms, and you know what? We didn't even check, but we'll do that now. We didn't even check the residuals, and let me first read in ggfortify here. Cool. And our object is going to be model 1. We'll get rid of the smooth color per usual, right? Because it's sometimes misleading. And then we'll get rid of the background here too. Okay. What do the residuals look like? Well, pretty bad, right? Pretty bad. We see major evidence of curvature, right? And so we know that based on the first plot, based on that first scatter plot we saw, where the line had a lot of curvature around it, that is a poor fit. We know that a straight line is probably not the best, right? And we see that reflected in the residuals too. So I'm not even going to look at the equal scatter. I'm not even going to look at the histogram either, because I already know that the goodness of fit is poor. It is not good. And we know that because the straight line here, if you were to look at this, just the single plot, and next to it put the original scatter plot we had, you'd see that it was the same kind of shape, right? These data are the same since we only have one predictor. Okay, so goodness of fit, not good. Not good. So what do we do? Well, why don't we model it quadratically? And I'm going to call this model 2. But we'll know that by looking at the formula of the linear model, this formula here, we'll know that it's quadratic because we have to kind of manipulate it in a different way. Same way that we saw up here in our plot, this situation, it's the same thing, right? This is the general terms. We need the data-specific terms. Okay, so how do we do that? Well, it's the same thing, dc.output, as a function of wind.velocity plus, we use this plus to denote that we want to add in another predictor. So we're not adding like the values together. We're just saying, and then, putting in another predictor. I, right? So it's going to treat the predictor as is in there. Wind.velocity squared. We do that by a little caret to the second power. Okay, and the data is still wind. We run that, and then we hit it with the summary.lm function again, summary.lm, and we run that. And then what do we see? Oh yeah, okay, here we go. So we see we now have 3 estimates. We have our intercept, negative 1.15, 1.16. We have our x1 slope, and we have our x squared slope. We have our x squared slope here. And we see that all of the p-values are significant. Since these p-values are less than 0.05, we can trust this estimate. We can say that, there's a good chance that the actual population has this intercept, and the actual population has this slope, and this slope for the squared term. Now, one thing that becomes very important to know and to realize is that when we start interpreting, these squared terms, it gets pretty difficult. We have to use some calculus involved, taking a derivative of blah, 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 blah. Who cares? I don't. So we're not going to so much worry about interpreting these kind of slopes. Okay, so it's no big deal. No big deal. But we know now that our model is doing a really good job, at least based on these p-values first. We'll take a look. R squared has jumped up quite a bit. It was in the 80s, like the lower 80s in the first model. We now see that it's jumped up to about 0.96, which is very good, and not a whole lot of difference between the adjusted R squared and the regular R squared. Well, so what's next in our checklist? Next is to check the residuals. So how do we do that? Well, just like last time, the ggfortify library is already read in, so we can just use this auto plot. And then the object is the second model that we've made. The smooth is going to be NA, and then we'll get rid of the background too. So we run that. How do the residuals look now? Nice. They look a lot better. They look a lot better, right? They're more spread out. There's not too much evidence of curvature, right? Something that we could live with, at least. And we see, maybe a little bit of clumping sort of on the upper end here, but that's okay. That's okay. This is something that we can live with. So now we'll check the histogram of the residuals. We'll see what that looks like. Okay, and we see something that's a little bit left skewed, just slightly left skewed, nothing too crazy, right? No major outliers, nothing that has like a gap in between bins or anything like that. So that's good. So this is a distribution of residuals that I can live with, Other people might not, and that's fine. That's fine if you can't. There might be a better model out there, but for the purpose of this, example, we can live with this. Okay. So now we have this regression equation that looks something like, let's see, dc, we'll just say power is some function of, and let me write out, I'm just going to go grab these real quick, negative 1.16 plus 0.72 minus, x, and then minus 0.04, we'll say, x squared. And that's what our regression equation looks like now. So if we wanted to figure out, and let me kind of pull up the old plot here, that quadratic scatter plot. Let's say that we wanted to predict, maybe we have kind of a gap in data from here to here. If we wanted to, we would just plug in, we'll say 4.5 or so for both of these x's, right? Not just one, for both of them. And then that will give us some estimate of power. And so it kind of makes sense too, right? If you think about wind turbines, there's a sort of sweet spot where they produce like an optimum amount of power. Now, I'm not an engineer, but it's my understanding that if the wind is not blowing fast enough, then the wind turbine blades won't be spinning very quickly and not producing a lot of power. And then if the wind is blowing too fast, then the blades start to either break, like there's a brake system within the turbine, or they begin to spin very quickly and or start to waste energy from like heat coming off of the turbine. So that kind of makes sense. Again, not an engineer, so don't at me, please. So it makes sense to model these data quadratically, right? And this applies to a lot of places, more than you think, right? Farming a lot of the time has this sort of quadratic behavior. If you're looking at, let's say, watering amount or like rain amount or something like that, and overall yield. If it rains too much, it's going to kind of drown out a lot of the yield. If it doesn't rain enough, obviously, then you won't have a lot of yield. And there's this sort of sweet spot for water, right? So it happens frequently. It's not, all the time. It doesn't make sense to always model things quadratically, but it does make sense to do it in this case, right? So one last thing that I want to do is show you just a small intro into multiple regression. Okay, so how do we do that? Well, it's pretty easy. It's pretty easy in this case. What we want to do is so we come back to our data, and what we want to do is make wind velocity, and then have another column of wind velocity squared. Okay? We're going to model it in the same way. Well, so how do we do that? Well, we just put in wind. The data from wind is going to get the data from wind again, right? So because we just want to add in, a new variable into our original data set. And then we're going to mutate a new variable, okay? I'm going to call it velocity. I'm going to call it VEL2, or velocity squared. And all that's going to be is just wind velocity, and see it kind of types it in there for you, caret 2, right, to the second power, or squared. And when I run that, we come back into the data, and we see now that we get 2.45 squared is 6.0, right, and some change. So now we have this new column. We have this new column of squared values, okay? So what we can do, we'll call this model 3. We'll call this model 3. And it's going to get a linear model made up of formula equals, okay, and then DC output as a function of wind.velocity plus VEL2. Okay, so it's doing the same thing as we did up here, except now we have a new column. We have a new column that we've made. And the data is going to be wind. Oh, hey, spelling is important. Formula. Okay, so we run that, and then we can hit it with this summary.lm again. Let me do this too. Before running that, I'll do the summary on the second model that we made too, because they should be identical. And we'll see here, if I pull this all the way up, we get an estimate of -1.5 for the intercept. Same thing up here too, for our model 3. In fact, you can pause the video, or if you're doing it yourself, you can kind of see. But how about instead, how about we do this? How about we look at the coefficients of each? And before I run that, okay, so I'm using this $ to look inside this object, this model object that I've made. Anything that has a list or like some kind of data frame, you can use this $, and it'll go into the components of it. And if I run both of these, we'll see here that we get the same coefficients. That means that we'll get the same p-values and the same r-squared and the same everything, right? Because we're making the same model, except we've just used this different column now. Okay, so what that is more or less just an intro into multiple regression as far as the form goes, the form of multiple regression, just using this plus sign and then some new column. And also, this is more or less an introduction into interaction. Okay, and interactions really are more or less just two variables sort of interacting, sort of covering the same ground, just maybe in different ways, and their relationship with our outcome, which in this case is this DC output. Now we will get into interactions in a future video because that stuff can get a little complicated sometimes. So we're not going to so much worry about it now, but this is essentially an introduction into all that. So I have nothing else here. Hopefully this was educational, easy, maybe, who knows. And if you have any questions, just let me know. Any comments, also just let me know. And I will see you next time.